said find T such that the matrix 1, -1, T, and 2 is not invertible. So there are ways of doing so, finding such value of T. One way would be by finding the determinant of this matrix. I'm not going to do that way right now. I'm going to do a much more elaborate way. I am going to compute the inverse of this matrix. So let's compute. Let's compute the inverse, which means that we form an augmented matrix. We write down this matrix, form the augmented matrix. The second block of the matrix is going to have the identity, the 2 by 2 identity. The first block has exactly the matrix we want to compute the inverse for. It has columns 1, -1, T, and 2. So we form that augmented matrix, and what we do next is that we want to row reduce. We want to row reduce. So to row reduce, I'm going to create a 0 on entry 2, 1. So I'm going to do the following row operation. I'm going to say row 1 added to row 2, and then we're going to replace row 2. The first row stays exactly the same. So in the first row we have 1, T, 1, and 0. The only thing that is changing is the second row. This is obtained, this row operation is really 1 times R1 plus 1 times R2. That's a linear combination of the rows with coefficients 1 and 1. So if we add those two rows, 1 plus -1 is 0. T plus 2 is T plus 2. 0 plus 1 is 1, and 0 plus 1 is also 1. So we obtain this matrix. The next thing I'd like to do is to create a 1 on entry 2, 2. Okay? So I'd like to create a 1 on entry 2, 2, and then this is where I have to make a note and say, look, if T plus 2 is different from 0, then I can divide by, I don't care. If it is a number, complex number, is different from 0, is not 0, then I can divide by this number. Then let's do 1 over T plus 2 times the second row. So the first row stays exactly as is. Everything on the first row is 1, T, 1, and 0. 0 divided by a number is 0. T plus 2, assuming that that number is not 0, divided by itself is 1. And then here we'd have 1 over T plus 2, and then 1 over T plus 2. That's what the second row looks like. Then, so far so good. I've created a 0 on the entry 2, 1, and I have created a 1 on entry 2, 2. What I'm going after making the first block to be as similar as possible to the identity matrix. The moment I get the identity there, I'm done. The second block would be the inverse matrix I was going after. Okay? And so I'm almost there because that matrix, the first column is 1, 0, and the second column is something 1, right? So what I would need is to make that something on entry 1, 2 to be equal to what? To what? I need that to be 0. I need to create a 0 there. But it's not too difficult, right? I could multiply the second row by that number. Could multiply the second row by that number, t times the second row. And then, in fact, you could do it in different ways, but I'm going to do it in this way. Multiply the second row by the negative of that number. Multiply the second row by minus t, and then add that to the row, the first row, and then replace row 1. Okay? So maybe I can do in red here such operation. So if I do that on the second row, in parentheses here, I have 0, and then this is minus t, and this is minus t over t plus 2, and this is minus t over t plus 2. Okay, so which means that here 0 plus 1, I'm substituting, the second row stays exactly as is, so I'm going to write 0, 1, 1 over t plus 2, 1 over t plus 2. And now the first row is going to be substituted, so 0 plus 1 is 1, minus t plus t is 0, which is exactly what I wanted, and then this number plus 1, here I have 1 minus t over t plus 2, and then 0 plus that number is minus t over t plus 2. Okay, and this is now looking the way I wanted it. So I now have successfully row reduced the first block of this matrix to make that block look like the identity matrix. And so the second block would be this matrix here, this submatrix here, this 2 by 2. This would be what the inverse of the original matrix is. But the question was not necessarily find the inverse of the matrix. The question was, what was the question? Find t. Find the values of t for which this matrix is not invertible, for which the inverse of the matrix does not exist. We could also say we can find the values for t for which a matrix is invertible, and in fact, this would be the inverse. That's kind of the expression we have. So the only thing that is messed up here, that could be messed up, is that that condition that we have. So if we had proceeded with the row operations, assuming t plus 1 is different from 0. Now, if t plus 1 is 0, if t plus 1 is 0, then the inverse does not exist. In other words, t plus 1 is 0. It's true if and only if t is negative 2. So if t is equal to negative 2, there is no inverse. However, if t is not negative 2, then the inverse, so if t is different from negative 2, then the inverse is that matrix we found there, which is first row 1 minus t over t plus 2 and minus t over t plus 2, and then the second row is 1 over 2 plus t or t plus 2, 1 over t plus 2. This would be the inverse if t is different from negative 2. Now, I said there is another way of answering this, of going about this. And the other way is that we could compute the determinant of this matrix. Okay, so we could compute the determinant of this matrix and then rule the values at which. So let's do it some other way. So another answer. So consider the determinant of the matrix 1 minus 1 in the first column, t, and 2 on the second column. Consider that determinant. And so for the matrix to be invertible, the determinant would have to be different from 0. If the determinant is 0, the matrix is not invertible, right? So, excuse me, we can say consider this. In fact, consider this equal to 0. If this is equal to 0, the matrix is not invertible. So this means the determinant of this 2 by 2 would be 1 times 2 minus 1 times t, and we're considering this equal to 0, which is 2 plus t equal to 0, and this is exactly a condition we have found. So t equals minus 2. In other words, if t is negative 2, then the determinant of that matrix is 0, which means the matrix is not invertible. So 0 determinant, I guess that's part of why this is good. It's good to review this. So determinant of a matrix equal to 0 means the matrix is singular or non-invertible. That another way of saying that is determinant different from 0 means the matrix is non-singular and it is invertible. For example, when we are computing eigenvalues, right? The definition of eigenvalue could be translated into a calculation that involves determinant, and that also brings into consideration the so-called characteristic polynomial.